Okay, thank you for the very kind and detailed introduction to me, and I'm going to talk about the title here. Try the realization of the numerical Turing tank test by Wall-Resolved Large Eddy Simulation based on 32 billion grid finite-element computation. Sorry, I think. Hold on a second, because my presentation is going on the automatic mode. I have to. Okay. I have to kill the mode off. Okay. Let me first introduce my team. I myself is a team leader, and Dr. Yamada and Mr. Nagano they're from Middle Information and Research Institute Incorporation, and they actually develop code and testing and doing so forth. Dr. Kumahara, he was a former researcher for RIKEN, but now he's in the JAXA. And Dr. Minami, they do algorithms, develop algorithms, and then also make performance optimizations. So most of the work I'm presenting here was their efforts. And finally, Dr. Nishikawa is from Shipbuilding Research Center of Japan. He actually does ship hydrodynamic simulations and also does the Turing tank test. What I'm going to present here is as follows. First of all, I'd like to briefly mention what kind of things we expect in the Fugaku era, which will start, I think, in the next month, and briefly explain what's the flow solver that we are using here, or we have optimized. And the code optimization and performance improvement is the main part of this talk. And then I will give two applications of the developed code, or optimize the code, and by that, I think you will have some idea or vision what we are going to be able to do in the Fugaku era, and conclude my talk. First of all, let me explain what is expected in the Fugaku era. I myself work for the industries, and in terms of industry, this is expected. First of all, repressing test is the main expectation for the high performance computing. And also, we like to understand unclarified phenomena. Design optimization based on the first principle simulation will also be done. And also, a bunch of data we are going to produce is going to be used for the reference as a reference data for developing improved reduced order model. But this talk will focus on the first one, repressing the test. Here's the actual Turing tank test, and they do the test every time they develop a ship. So tank is 400 meters long and 18 meters wide. And the mothership, which is about 6 meters long, is told about the maximum speed of 50 meters per second. We'd have to replace this kind of test because once we could do that, the designer has to redesign their product as soon as the design is complete. So in that sense, this has been a long-term dream of all engineers and also researchers. So apparently, the simulation here is concerned with the Navier-Stokes simulations as the previous research is. I think it is also concerned with the Navier-Stokes simulations. So currently, people in the industry mostly use Reynolds average Navier-Stokes, abbreviated RANS, and RANS model effect of terminal eddies and wall scales, and maybe tuned for a particular flow, but it doesn't necessarily guarantee the same level of accuracy when it is applied to a different flow. The wall-resolved large eddy simulation. Large eddy simulation means that we simulate terminal eddies in the boundary area, which is responsible for the production of turbulence, and wall-resolved, meaning that we resolve everything we need to resolve. And this gives us accurate result at the DNS, which is a direct numerical simulation data, with about 1/100 times less or smaller cost. This is expected to become a complete substitute alternative for testing. So here's some example where the weight profile of a shape is predicted by length. And when length is tuned, as you see, with a comparison between the experiment and length, the match between the two is very good. However, this is a result obtained by a different length model, and a different length model shows a different result, which means that length does not necessarily guarantee the same level of accuracy as it is tuned for a particular probe. To the contrary, or on the other hand, if you do properly the wall-resolved large eddy simulation, the match between the experiment and simulation is quite perfect. Here's another example where we predicted the wake of a different ship by the wall-resolved large eddy simulation and compared with the experimental data, and once again, the match between the two are perfect. So, as you have seen, just for two cases, still, I'd like you to be convinced that the wall-resolved large eddy simulation, when it is applied properly, guarantees accuracy at all the times. All right. But here's some essential difficulty for the application of this method. For instance, what you're seeing here is a transitional boundary that develops on the flat plate. And as we are seeing here, the eddy structures, well, the size of eddies is very small compared to the length of the plate, which means that the high Reynolds number wall-resolved large eddy simulation requires billions of gates. But on the other hand, we have had a great increase in the performance in the supercomputer, like we had a K, which started its full operation in 2012, and K had a computer node with a peak performance of 128 gigaflops and achieved 10.51 petaflops without impact. And after several years, almost 10 years, we have Fugaku to start its full operation just in this April, or I think in this March. And Fugaku has a computer node with theoretical peak performance of roughly 3.4 teraflops, and has already achieved. So this is the previous number presented in July last year. I think it is already 422 petaflops. But anyway, the computer node performance has been improved by a factor about 26, and overall performance by a factor of I think a little more than 40 if you use the latest number of 422 petaflops. Okay, with all of this in mind, our goal here is to substantially shorten the time for the wall-resolved eddies by a factor at least 30, I'm sorry, or more, and to realize the numerical Turing tank test. So this is what we are going to do, and I'm going to explain what the flow solver is. We have been developing a flow solver called Francois Blue, hereafter abbreviated as FFB, and this is finite element-based flow solver and can be applied for incompressible and compressible flows. And developed in particular for the industrial application of the wall-resolved areas. And the code has many features, but among many others, two of the features is automated mesh refinement function, because people cannot produce the mesh composed of, say, 32 billion gate by hand. So we have automated mesh refinement function, and also the overshoot method. The overshoot method is needed for computing interaction between the stationary pad and rotating pad, as you're seeing in the marine proper case on the right bottom hand case. Okay. It is based on the Navier-Stokes equations. Here, what is presented here is the incompressible governing equation. We have a slightly different governing equation, and also completely different algorithms for the compressive flow solver. And solution algorithm is based on the Clark-Nicholson method and fractional step. And first of all, we compute, we compute the velocity predictor by using equation 3, and then update the pressure by solving the Poisson equation represented by equation 5, and finally update to obtain the velocity vector at the next time step by equation 4. Here's the main structure of the code. Each of the M-type processes is dedicated or computing each of the domain, d-domain, and boundary condition data, and define initial flow field data, and compute element methods, and enter the time match loop, and end the time match loop when the specified number of time steps has been computed. And finally, write the final flow field. And similarly to the previous talk, we do not have any intensive data I/O. We finally write the flow field data. And among this flow structure, more than 99% of the time spent is spent in the time match loop. And therefore, optimization is focused on the main kernel that does the operation in the time match loop. Front for Blue is a very large code, but composed of only 4 hot kernels, starting with grad 3D, grad 3X kernel, which computes a pressure gradient at a node. And then the field 3X2 kernel computes the divergence of the velocity, as well as that of the pressure gradient. And grad 3D1 compute right-hand and left-hand side of the Navier-Stokes equations. And finally, the X3 kernel does the matrix vector multiplications. And these are the kernels that we have optimized, and among these kernels, I am going to explain how we did it by taking the grad 3X kernel as an example. Let me first mention what is the typical operations and also the essential bottlenecks associated with the operations. The typical operation we do, or finite element flow solver do, is a matrix vector multiplication. In this case, it is done by the X3 kernel and superposition of the element vector to the global vector, and also that of the element matrix to the global matrix and the inner product. And on the other hand, it is a very high byte-5 proofs ratio between 2.5 to 4, depending on the kernels. And apparently, this is a memory throughput bound code, bound kernels. And the vector elements are referenced by a list vector. And here is a point where the bottleneck, the first bottleneck is identified, which is the array element in general is referenced by a list vector. And scattered, and the data is scattered in the memory space, and which results in normally very frequent L1 data cache and L2 cache miss occurrences. Let me skip that. I'm sorry. The second thing we like to mention is in the conventional finite element flow solver, everything is done in the element-based loop. And therefore, for this case, the residuals computed in the element loop is superimposed to the node that composes the element. On the other hand, the general feature of the latest CPUs are as follows. First of all, the number of floating point registers has become smaller. For instance, K had 128 floating point registers, while Fugaku had only 32. And latency has increased in terms of its cycles, and the longest single bit, like 128 bits of K to 512 bit to Fugaku. So if you consider all of these, the instruction scheduling has become more difficult. And in particular, if you superimpose, let me change the pointer here. For instance, if you compute the residual in this element, and this is store the residual vector to this node, and this operation is generally called the scatter store. And if you the scatter store significantly increases the L1 data cache busy time, so we like to avoid that, and we did it by a completely new loop structures. For the first bottleneck, which is the data is scattered, like here, I'm not explaining the detail what this graph means, but this is representing how the data is scattering in the memory space. And to avoid that, we have reordered the node numbers. And firstly, we subdivided the entire domain into smaller blocks, a number of smaller blocks, and sequentially number the node in each of the blocks in some algorithms, and which resulted in a very clustered data referencing relations, as you were saying on the bottom, on the right bottom. So this data structure has been reduced to this data structures, which has given us 11 times speed of one of the kernel, main kernel, correct 3 kernel on K computed. The other thing we did is the invention of the complete new loop structures. In the classical finite element flow solver, everything has done in element-based loop. For instance, conventionally, we first compute the residual in the element 1 and then element 2 and element 3 and so forth, but which resulted in a scattered store. Therefore, we have completely changed the loop structure. In the new loop structure, we have computed the residual in the node 1 and then node 2 and node 3. And in this algorithm, no scattering, scattered store is taking place, and resulting in the 5 times speed up one of the main kernels, which is grad 3x kernel on Fugaku. So these are typical things we did. However, we did many other things, which I'm not explaining here due to the time that I have for this presentation. Let me explain how much performance improvement we have obtained. In particular, focusing on the grad 3x kernel. This is the time spent by the 12 thread running on one CMZ on Fugaku. The original code spent 45 seconds, but this kernel, the optimized kernel, spent only 9 seconds, which means that we have had the 5 times speed up. And in particular, this bar is corrected memory visit time. So you understand that the time spent for the memory visit time is almost the same for the execution time. So that means that throughput has achieved, we have achieved about the maximum possible throughput by the optimization I just mentioned. Here the sustained throughput of the 4 main kernel on K, denoted by the white bar or white box, and K for the optimized kernel by the red, and Fugaku on the blue for the optimized kernel. And I'm sorry. Here is the maximum possible throughput represented by the stream triad benchmark for K, which is 46.6 gigabytes per second. And on Fugaku, I'm sorry, which is 20 gigabytes per second. So compared to this maximum possible throughput, we have achieved on both K and Fugaku about the maximum possible throughput, even higher, a little higher throughput on K. We have tested the optimized code on many platforms, but before explaining that, I like to explain what kind of performance we have obtained on Fugaku. Let me focus on Fugaku only. And here is the performance represented in gigaflops for one single node. And the performance ratio to the peak is about 4.5% to 7.8% of the peak, which is approximately the ideal performance we can obtain. And as I mentioned, we have tested the performance in many other platforms, including Intel and AMD, as well as NEC. And on Fugaku, we have achieved about 180 gigaflops performance. Finally, let me explain the result of the weak scale benchmark test made on Fugaku. We have used up to about 7.6 million cores, almost entire cores. And we have achieved 22.6 petaflops, which corresponds to 4.3 of peak performance in the double precision peak. And so here's the performance we have obtained on Fugaku. And finally, I'd like to mention what kind of things we can do with the performance we have achieved. I am showing two examples of the industrial application of the developed optimized code. The first one is the ship hydrodynamics and related to numerical towing tank test. Here is one example of the simulation. We have used 32 billion grids to resolve the smallest bed activated in the turbine boundary area on the hard surface. Here the vertical structures appearing, which is appearing near the center of the ship. And if you look at a little closer of the eddy structures, actually we have captured small eddy that's small as 700 micrometers, which is very small compared to the length of the ship, which is about 6 meters. And of course, we have to have quantitative comparison, and we have tested many methods. I'm just showing one such examples, and experimental data is shown by the red symbol, while the simulation is shown by the green symbol. And our target is this point, the maximum Reynolds number point, and the error, or the difference between the simulation and experiment is only 0.36%, which is well within the measurement uncertainty of about 1%. Here's some other example of the application of the code. And here we call wave making resistance test. What you're seeing here, this is caused by the small eddies that we have computed in the boundary. So here, the eddy structures or the boundary area and free surface interaction are simulated simultaneously. And finally, we have done some other very important tests called the self-propulsion test. And self-propulsion test is made to know the effective interaction between the rotating propeller here. This is a rotating propeller, and this is rudder. And this is the near stem part of a ship. And I think, well, I believe that you understand how small the eddies are in the boundary area compared to the overall length of the ship. Also, the ship is only visualized in the stem part. Here are the numbers that we actually predict. And I'm not going to explain each of the number in detail, but I like just so you focus on the number here with the percentage mark. And here is the relative error between the experimental data. Experimental data is shown on this black line because in the experiment, we only know the average, the body, but in the simulation, we of course know the fluctuating body around the average. And comparison, the difference is well within the prediction tolerance of, in this case, 3%. And here the bottom line, whether or not we could build a numerical towing tank on the K computer era. The one case had taken about 2 days, while it is only 37 minutes. So this is one example or one proof that the numerical towing tank could actually be built within several years. All right, but the simulation of this kind not only provide you the number to replace the test, but also provide you very detailed information about flow structures. And for instance, what you're seeing here is a flow around the propeller subject to the hull wake, and this kind of information can be used for improving the propeller performance in this case. Let me add, if I have some time, some other example. This is a numerical wind tunnel test. This is not the towing tank test for automobile air acoustics. Simulation of the interior noise is very important because if you could simulate the interior noise very accurately, the people in the automobile do not have to produce an actual test car. Actually, production of one test car costs about, I think, 300 million yen or $2 million roughly. So people actually avoid to produce a test car. And once you produce a test car, and if some noise it has become a problem, you have to change the design completely. So people actually avoid that from taking place. And here is the wake structure around here. This portion is called the A pillar, and this is side mirror. And in this case, the flow separate at the A pillar and reattach it on the side window and produce a very complicated and dominant source of the noise in this case. So we would like to simulate that. And for doing that, we have simulated external flow and also simulated panel vibration of the car, because in this case, noise is transmitted through the panel vibration of the car. And we compared with the data in terms of the panel vibration as well. And here the green lines are from measurement, and red lines are from prediction. And we have had, I think, reasonable or satisfactory agreement between the two. And finally, we have predicted the interior noise sound spectrum, where the simulation is plotted by the green bars, where the experimental data is plotted by the red bars. So until around, I think, for instance, 2 kilohertz, the measurement between experiment and simulation is very good. We haven't used any empirical constant to produce this data. So this kind of thing we'll be able to do in Fugaku era by in about an hour or so. So recently, we also simulated external acoustical field by using the simulation data that is produced by the wall-resolved areas. And finally, let me mention this one. And here, by looking at this kind of simulation, you understand that how the noise is actually generated from very complicated underfloor flow and produced or radiated in this direction. And people like to very much know this kind of information that could never be obtained by the conventional experiment. So this is all I like to say, and I like to conclude by saying a finite element flow solver named front blue has been fully optimized to completely replace the barrier test made for the final evaluation of the flow-related industrial project. And essentially, new algorithms have completely eliminated scattered source, and the optimized content has achieved a sustained performance, throughput very close to the effective hardware limit. I'm mentioning the stream trial 3 benchmark data. The optimized whole code runs by about 30 times faster on Fugaku and achieve a single node performance of roughly 180 gigaflops on Fugaku, which corresponds to 5.3% of the peak. And finally, FEB has achieved a sustained performance of 22.6 petaflops with roughly 7.6 million cores in the Wall-Resolved Large Eddy Simulation that uses 30 billion element has been significantly shortened from almost 2 days on the K computer or in the era of K to only 37 minutes on Fugaku or Fugaku era. I'd like to finally acknowledge the support from the MEX for sponsoring this project and providing the computation resources both on K and Fugaku. And Fujitsu Limited has made very good technical support, and finally, I'd like to mention many of the industry partners listed here. That's all. Thanks.